Hello students, now we are going to start a new chapter, P block elements. First, group 15 elements, which is known as the nitrogen family. Group 15 includes nitrogen, phosphorus, arsenic, antimony and bismuth. As we go down the group, there is a shift from non-metallic to metallic through metallurgic character. Nitrogen and phosphorus are non-metal, arsenic and antimony metalloids, and bismuth is a typical metal. Electronic configuration. The valence shell electronic configuration of these elements is NH2 NP3. The s orbital in these elements is completely filled and p orbitals are half filled, making their electronic configuration extra stable. Atomic and ionic radii. Covalent and ionic radii increase in size down the group. There is a considerable increase in covalent radius from nitrogen to phosphorus. However, from arsenic to bismuth, only a small increase in covalent radius is observed. This is due to the presence of completely filled d and or f orbitals in heavier members. Now, ionization enthalpy. Ionization enthalpy decreases down the group due to gradual increase in the atomic size. Because of extra stable half-filled p orbital, electronic configuration and smaller size, the ionization enthalpy of the group 15 element is much greater than of group 14 elements. The order of successive ionization enthalpies as expected is enthalpy 1 is less than enthalpy 2 and less than enthalpy 3. Now, electronegativity. The electronegativity value in general decreases down the group with increases atomic size. However, amongst the heavier elements, the difference is not that much pronounced. Now, physical properties. All the elements of this group are polyatomic. Dinitrogen means N2 is the diatomic, while all others are solids. Metallic character increases down the group. Nitrogen and phosphorus are non-metals. Arsenic and antimony metalloids, and bismuth is the metal. This is due to decrease in ionization enthalpy and increase in atomic size. The boiling points in general increases from top to bottom in the group, but the melting points increases up to arsenic and then decreases up to bismuth. Except nitrogen, all the elements show allotropy. Now, chemical properties. First, oxidation states. The common oxidation states of these elements are -3, +3 and +5. The tendency to exhibit -3 oxidation state decreases down the group. Bismuth hardly forms any compound in -3 oxidation state. The stability of +5 oxidation state decreases down the group. The only well characterized bismuth compound is BiF5. The stability of +5 oxidation state decreases and that of +3 state increases. Nitrogen exhibits +1, +2 and +4 oxidation state also when it reacts with oxygen. Phosphorus also shows +1 and +4 oxidation states in some oxo acids. In the case of nitrogen, all oxidation states from +1 to +4 tend to disproportionate in acid solution. Now, anomalous properties of nitrogen. Nitrogen differs from the rest of the members of this group due to its smaller size and high electronegativity, high ionization enthalpy, and non-availability of d orbitals. Nitrogen has unique ability to form p-pi multiple bonds with itself and with other elements having small size and high electronegativity, as for example carbon and oxygen. Heavier elements of this group do not form p-pi bonds as their atomic orbitals are so large and diffuse that they cannot have effective overlapping. Nitrogen exists as a diatomic molecule with a triple bond, one S and 2p bond. Between the two atoms, consequently, its bond enthalpy is very high. On the contrary, phosphorus, arsenic and antimony form metallic bond in elemental state. However, the single nitrogen-nitrogen bond is weaker than the single p-p bond because of high interelectronic repulsion of the non-bonding electrons owing to the smaller bond length. As a result, the catenation tendency is weaker in nitrogen. Another factor which affects the chemistry of nitrogen is the absence of d orbital in its valence shell. Besides restricting its covalency to 4, nitrogen cannot form d-pi, p-pi bond as the heavier elements. Phosphorus and arsenic can form d-pi and p-pi bond also with transition metals when their compounds like P C2H5 thrice and AC6H5 thrice act as ligands. Now, reactivity towards hydrogen. All the elements of group 15 form hydrides of the type EH3, where E is nitrogen in P, A is arsenic, Sp antimony, or Bi bismuth. E is equal to N, P, A is Sp or Bi. Some of the properties of these hydrides are shown. The hydrides show regular graduation in their properties. The stability of hydrides decreases from NH3 to Bi means bismuth, BiH3 bismuth hydride, which can observed from their bond dissociation enthalpy. Consequently, the reducing character of the hydrides increases. Ammonia is only a mild reducing agent, while BiH3 means bismuth hydride is the strongest reducing agent amongst all the hydrides. Basicity also decreases in the order of NH3 greater than PH3 greater than ASH3 greater than SbH3 and greater than BiH3. Now, reactivity towards oxygen. All these elements form two types of oxide, E2O3 and E2O5. The oxide in the higher oxidation state of the element is more acidic than that of lower oxidation state. Their acidic character decreases down the group. Their acidic character decreases down the group. The oxides of the type E2O3 of nitrogen and phosphorus are purely acidic. That of arsenic and antimony amphoteric, and those of bismuth is predominantly basic. Now, reactivity towards halogen. These elements react to form two series of halides, EX3 and EX5. Nitrogen does not form pentahalide due to non-availability of d orbitals in its valence shell, and pentahalides are more covalent than trihalides. All the trihalides of these elements except those of nitrogen are stable. In case of nitrogen, only NF3 is known to be stable. Trihalides except BiF3 are predominantly covalent in nature. Now, reactivity towards metals. These elements react with metals to form their binary compounds exhibiting -3 oxidation states, such as Ca3N2 means calcium nitride, Ca3P2 means calcium phosphide, Na3AS2 sodium arsenide, Zn3Sb2, zinc antimonide, and Mg3Bi2, magnesium bismuthide. Now, nitrogen N2R dinitrogen. Preparation. There are many types to prepare N2 here. By heating a mixture of NH4Cl and NaNO2, N2 is collected by the downwards displacement of water. And second reaction of preparation of dinitrogen is given here, and third reaction also is given here. Now, industrial method of preparation of dinitrogen, nitrogen from liquefied air by fractional distillation. The boiling point of nitrogen N2 is minus 196 degrees Celsius and that of oxygen is minus 183 degrees Celsius, and hence they can be separated. From producer gas from furnace, producer gas is the mixture of CO and N2. When the mixture of CO and N2 is passed over heated CuO, the CO gas is oxidized to CO2, which is absorbed in alkalis, and N2 means dinitrogen remains, which is collected in gas cylinder. Properties of dinitrogen. N2. N2 is a colorless, odorless gas which is insoluble in water. It is non-polar, covalent and neutral molecule. It is neither combustible nor a supporter of combustion. It is absorbed by heated magnesium and aluminum. The nitrates formed thus react with water to form ammonia NH3. Reaction of hydrogen at 200 atmosphere and 500 degrees Celsius and in the presence of iron catalyst and molybdenum promoter, N2 combines with H2 reversibly to form ammonia. The process is called Haber's process and is the industrial method of manufacturing of ammonia, and this reaction is exothermic. Reaction is N2 plus 3H2 equal to 2NH3. Now, compounds of nitrogen, ammonia. Preparation. By the action of any base or alkali on any ammonium salt, ammonia is produced. NH4Cl plus calcium hydroxide gives ammonia and water and carbon dioxide. And With the reaction of NH2CO, NH2 urea with water, ammonium carbonate is obtained. Now, industrial methods of preparation. Haber's process, N2 plus 3H2 with reaction at 500 degrees Celsius and 200 atmosphere, ammonia NH3 is obtained. Now, properties of ammonia. Colorless gas, lighter than air, being basic in nature, turns red litmus blue, and it acts as a Lewis base. Highly soluble in water, the solution is called ammonium hydroxide solution, and Na plus NH3 on heating NaNH2 plus half H2 is obtained. Amides decompose back with water to form ammonia and sodium hydroxide. Now, uses of ammonia. Used as a refrigeration fluid. Second, for the production of ammonium fertilizers such as ammonium sulfate, ammonium phosphate, ammonium nitrate, urea, etc. Third use, for removing grease because NH4OH dissolves grease. For manufacturing of HNO3 nitric acid by the Oswald process. And fifth property is as a laboratory reagent. Oxides of nitrogen. Nitrogen forms a number of oxides, as for example N2O, NO, N2O3, NO2 or N2O4 and N2O5, and also very unstable NO3 and N2O6. All these oxides of nitrogen exhibit PF-PF multiple bonding between nitrogen and oxygen. Now, properties of oxides of nitrogen. Oxides of nitrogen are all oxidizing agents. N2O even supporting the combustion of sulfur and phosphorus, and NO, which is thermally more stable, supports the combustion of magnesium and phosphorus but not of sulfur. Sulfur flame is not hot enough to decompose it. Now, nitric acid HNO3 preparation in laboratory. Reaction of NaNO3 and H2SO4 gives NaHSO4 plus HNO3. HNO3 is now almost exclusively manufactured by Oswald process. In this process, ammonia is catalytically oxidized NO over a platinum rhodium catalyst at 1200 Kelvin. Properties of nitric acid. Pure nitric acid is colorless liquid. It decomposes readily in light, giving a yellow color due to the formation of nitrogen dioxide. It is a strong acid and is almost completely dissociated into ions in solution.